protection in a general purpose operating system based on monolithic kernel design. We think that, well, if Microsoft did at least that, if they establish a third-party driver verification authority, which would be required for all developers always to send a driver then in a form of source code at best, and only after they evaluate it, they give a certificate, that would increase the bar a little bit. It would rise the bar a little bit, sorry, but it will not solve a problem. Okay, second part of this presentation. Please make distinction between the first part and the second part. Last year, I also gave like two-part presentation. People were like confusing Bluepill with pageful attack. So these were all about how to load stuff into Vista kernel, which officially does not allow to load stuff which is unsigned. So once we have this ability, let's think about how we can subvert it. Our original idea was to also talk about type 2 and its subversions at this lecture, but because we already have 120 slides, I decided to skip this part. So we will go directly to virtualization-based malware. We're gonna do a little intro, 5 minutes, and then we will talk about, we spent like half an hour talking about detection. And then we will talk about nested scenarios and why they are actually important. Yeah, that's very easy. We have software and hardware virtualization. Software basically is what is currently mostly used. Hardware is what is actually coming. And Bluepill, the malware I presented last year, made use of hardware virtualization. The nice thing about hardware virtualization is that it allows to create very thin hypervisors in a very easy way, at least at the beginning. I make a distinction between full VMMs and thin hypervisors. Full VMMs are interested in emulating or virtualizing the whole system together with all the I/O, with all the devices. However, the thin hypervisors are interested only in controlling the system in a stealthy way. Original Bluepill was presented here last year by me. Also, Dino Daizovi presented Vitriol, which was, while Bluepill was implementation on AMD SVM, Dino's rootkit was implementation on VTX, on macOS, I think. In May 2007, after I started the company, we decided to redesign and write from scratch the new Bluepill, which implements many new features and also has a completely new design. Design in terms of like it uses HVM layer similar to Zen, so it allows, hopefully it will allow to easy port it to VTX architecture. Currently we only port it to SVM. The idea of Bluepill, probably everybody knows, is just we have the operating system running. Attacker somehow gets his code into the system. The code is executed, the code creates a virtual machine, and then moves the native operating system into a virtual machine. Itself becomes a hypervisor and resumes the guest. And the assumption is that the guest cannot actually realize that actually it has just been moved to the virtual machine. The whole process takes like 1 millisecond on the fly. So SVM is just a set of instructions, like a couple of more instructions added to ISA of PC architecture. In order to use them, we need to set SVME bit in ether register. And this is the most important probably thing when we consider SVM detection methods, because all of them will be actually trying to exploit this fact that SVME is set and that a malicious hypervisor is trying to hide this fact. Just like 10 days ago, AMD released another a new specific update of its manual, where they released a new specification of SVM. It has an additional layer of security for enabling SVM mode, which you see. Okay, basically it's like we have a special register, like a password register, where we can put a value, and then this value is like cannot be read anymore. And then if anybody wants to set the SVME bit in ether register to enable SVM, he or she needs to know the password first. However, one more solution that has been added over the last months was more and more computers have an option in BIOS that allows you to disable virtualization. For example, yesterday we had a training, and we found out that actually the machines that were delivered for the training had actually virtualization disabled in BIOS. However, we don't believe that virtualization disabling is a proper way to protect against like blue pill-like threats. Just because virtualization has lots of legitimate usages, it's a great technology. For example, Virtual PC 2007 already uses hardware virtualization extensions. And in the next 2 years, we'll probably see more and more applications making use of hardware virtualization. So basically, disabling virtualization is basically like saying, let's disable your network card so you'll be avoiding network attacks. This is how SVM is normally used. It's just the VMrun instruction is the heart of SVM model. From this slide on, I focus on AMD SVM architecture. There's mapping almost one-to-one between VTX and SVM, but we focus on SVM just because we are familiar with this, and we are familiar with this just because we have a couple of machines to do the tests on. So normally we just fill a VMCB block, which describes the guest and what we want to intercept in the guest. VMrun creates for us a hardware virtual machine and starts executing it until an intercept occurs inside a guest. And then the execution is coming back up the instruction after the VMrun. This is how the blue pill idea, this is the presentation of blue pill idea. So what we do is just at some point of time, we just So basically, we've somehow managed to get our code executed by the native operating system. Our code just enables SVM, prepares VMCB in such a way that this VMCB actually duplicates the state of the currently running operating system, and then executes VMrun. However, RIP, the instruction pointer register, we make it point to read instruction from this function. Then we call VMrun instruction. We execute VMrun instruction, which basically creates a virtual machine, starts executing from IP address, which is the read address. So basically, it starts executing all the instructions after our call blue pill inside the virtual machine. So basically, we resume the guest. However, the guest is now executing inside the virtual machine. And we here becoming a hypervisor. Nothing couldn't be actually simpler than this. The whole point is, this all happens on the fly. There is no reason to reboot the system. We don't have to modify anything inside MBR or whatever. We do not virtualize any hardware. We are a very thin hypervisor. We allow all the I/O to go through. So there should be no performance impact. If you have your favorite 3D graphics card, it still be supported after you load blue pill. Okay, detection. Before we move on to detection, let's do a very important distinction. After I presented blue pill here last year, there were a couple of people releasing papers, about maybe almost 10 different papers. Everybody was blue pill detection. However, all they did actually was AVMM detection or SVM detection. So please distinguish between detecting the presence of a VMM, like a virtualization or SVM mode, from detecting the actual virtualized malware. This will probably become more evident for you when we go to the nested virtualization at the end of the presentation. Just keep in mind this distinction for now. Okay, I'm going to exaggerate just to illustrate the difference for you. It's like the SVM detection, if we say that it's equal to blue pill detection, is almost like if we said that we can detect a botnet agent by looking at the executable, and if the executable actually makes use of a network, then it's a botnet agent, right? This is a little bit exaggeration, but hopefully you get the point, and we'll get to this later when we talk about nested stuff. So let's focus first on this one, because it's still interesting. Well, of course, we have timing analysis. We have lots of, actually, instead of just talking about this, I'll just move on there. So let's use timing analysis first. As I said, because we need to set this SVME bit in if register to enable virtualization, so basically, Blue Pill probably would be interested in actually cheating about this bit being set, just because if it did not, then we would just look at the if register and see, SVME bit is set, this is suspicious. So probably would be interested in cheating this bit. So the simple way of detection is just, well, not surprisingly, there's a read FR instruction, which is used to actually get the value of if register. So not surprisingly, the read if register on a clean system takes like about 100 cycles. However, on a system with the Blue Pill installed, it takes like, for example, 2,000 cycles, or in case of our Blue Pill, like 10,000 cycles, because our Blue Pill is pretty complicated. By the way, lots of people are saying that actually you can use CPU. So all the methods are using readMSR ether because people know that if there is a like Blue Pill or something, they will be intercepting readMSR ether. However, lots of people suggest that CPU ID instruction is something that is always intercepted. This is not true. We actually do not intercept CPU ID instruction, and we cannot do this perfectly. So well, we can intercept CPU ID, but we don't have to do that. The only thing right now we have to do, if you want to cheat about SVME, is to intercept readMSR ether, not CPU ID. If somebody tells you that CPU ID must be intercepted, then probably they have experience with VTX only. I'm sorry, we're gonna do questions later because we're really speeding now. So. This is just some examples. As I said, clear 100, Blue Pill like about 10,000. So how can we measure time? Well, we can obviously use a timestamp counter using read TSC instruction, which is the best for measuring like execution time of an instruction because it has a great resolution. We can maybe use HPET timers as well, but which also have very good resolution, but they are still local. We can use real-time clock, which is also a local device. However, it has a very poor resolution, and eventually we can use NTP protocol to get trusted time, because not surprisingly, all the first three can be, I'm not saying trivially, but relatively easy cheated. For example, HPET timer, which generates interrupt, is quite easy to actually cheat because we can basically intercept and interrupt, which is a standard operation in SVM. So let's start with read TSC cheating. Last year when I was giving this presentation, I told you that you can actually use TSC offset. This is what documentation says actually, and even today we saw a presentation on Virtual 2008 server, and they said that they could use TSC offset maybe for virtualization. However, this doesn't work well, just because the variation, like sometimes readMSR FR would take 8,000 cycles, sometimes 10,000 cycles on a Blue Pill machine. So we don't really know what's the good value for TSC offset. So basically, it's not really precise. So we can, if we just decided to put like minus 10,000 in 9,000 in TSC offset, sometimes we would be getting a negative timing for an instruction, which would be pretty suspicious. So that's why we came up with this simple, funny method of cheating read TSC, which is based on some anti-debugging techniques, quite popular in Russia, I guess.